There's Hurricane Wilma has strengthened back to a Category 3 after slamming into the Yucatan.
Okay, here we go again, guys. Come on. Let's stay on it. Capture that, capture that. No! Quick scoper! What did I say? Get her, get her, get her! Wait, what? Hey John, how's it going? Have you lost power as well, man?
Yeah, we lost everything. Internet as well. I don't know what's going on. I wonder if the whole unit blocks out.
Hi James, what have you been up to?
I was just checking the footy scores.
Oh, bejeebers, where'd you come from?
Hey boys, I'm Liam from Energex.
That was unrealistically prompt.
So, you boys having trouble with this blackout?
Yeah mate, the whole unit's down. Any idea what's going on?
Well, from what I heard, one of the main transmission lines that leads power to this area, their connection failed.
Oh wow, how could something like that happen?
Well, with winds like this today, it's possible that an undamped transmission line could have experienced significant vibration, which led to the failure of the line.
Unreported transport crimes? What does that have to do with anything?
Oh, nothing, mate. I said undamped transmission line.
Ah, what's that?
Oh, it's a fair question, mate. How about we watch this precise yet informative video?
Welcome to Advanced Dynamics for Dummies. For this week's project, we investigate a method for reducing Aeolian vibration in power lines. Power transmission lines carry high voltages of up to 275 kilovolts through steel cables suspended by support towers. With high voltages comes a high danger factor, as a fault in these lines can cause shorts, blackouts, and potentially fires. A terrifying example of this is the Black Saturday bushfires in Victoria, where vibration led to the fatigue failure of power lines which sparked fires. High winds generated by storms or cyclones are a major contributor to the vibration. Therefore, it is important to control the vibrational behavior of power lines in the uncontrollable environment. The type of vibration that causes the most damage is Aeolian vibration. Aeolian vibration is caused by vortex shedding. Under moderate wind speed, von Karman vortex shedding will induce vertical vibrations at frequencies depending on the Struhl relationship. Aeolian vibration's high frequency causes accelerated fatigue damage to the supports on the towers, as well as fraying the cables themselves. Frayed cables eventually snap at the supports, which results in fallen power lines. For these reasons, power lines must be engineered to be highly durable. However, fatigue failure due to vibration is difficult to prevent purely with intrinsic cable properties. A Stockbridge damper is one way of suppressing this Aeolian vibration to ensure minimal fatigue damage to the cables. The vibration of the messenger cable and blocks absorbs the vibrations from the powerline cable. Modern designs use masses of steel. The powerline cable and Stockbridge damper system is nonlinear. However, simplifications of the system can be made in order to allow for easier optimization of the damper. The Stockbridge damper can be modeled analytically as a dynamic vibration absorber. Dynamic vibration absorbers are used for suppressing steady-state amplitudes at resonance. They consist of a secondary mass attached to the primary system mass by a secondary spring. For the free body diagram, the combined equations of motion can be constructed. During steady state, the vibration amplitudes for the cable and the Stockbridge damper will be in the form of a sine wave. Therefore, the acceleration of the displacements can be found and substituted into the equations of motion. By inverting the frequency equation matrix, an equation for solutions to the amplitude of the cable's vibration is acquired. The most important result of this analysis is that the amplitude of the cable can equal zero. This would theoretically occur when the amplitude of the forcing frequency matches the uncoupled single degree of freedom natural frequency of the Stockbridge damper. According to this analysis, the Stockbridge damper should be tuned to the forcing frequency on the cable, which is produced by the wind. In order to verify results from the experimental and simulation models, the undamped cable natural frequencies can be calculated using string and beam theories of transverse vibration. The beam solutions are useful for comparison with a strand 7 finite element model, which uses beams.
Cheers, man. Even as a civil engineer, I understood that.
Oh, no worries, mate. Well, that's all well and good, but do they actually work? Yeah, mate, have a look at this.
Welcome back to part 2 of Advanced Dynamics for Dummies. In this video, we investigate whether Stockbridge dampers can reduce Aeolian vibration in practice. I'll hand over to our computer expert Jacob to discuss how he simulated a Stockbridge damper and what he found.
To simulate the effects of a Stockbridge damper, a model of the system was constructed in strand 7. This model was represented using beam elements with pin-pinned boundary conditions, and the grid was refined until the natural frequencies converged to the analytical solutions obtained for a beam model, both as a sanity check and to ensure the model was behaving as expected. Once the generic model of our cable was represented, our goal was to demonstrate the effects of the damper with an oscillating force applied to the cable. As the theory suggests, if the uncoupled single degree of freedom natural frequency of the damper and the forcing frequency are equal, the cable's amplitude of the vibration will drop to 0. To show this, a symmetrically stiff damper was constructed using 3 spring elements, with axial and translational stiffnesses arbitrarily chosen, but with appropriate engineering judgment. The natural frequencies of the system were then solved, and the natural frequency corresponding to the mode shape where the damper was oscillating, but no cable oscillation occurred, was used as the forcing frequency to demonstrate the damper's maximum effect. Using the nonlinear transient dynamic solver and selecting the appropriate time steps for the solution iteration, as well as constructing a factor versus time table, which provides information to Strand on how the load should oscillate in time, the solver can then be run. The simulation results are presented before you now. On the left, an external force with a frequency equal to the natural frequency of the damper is applied to the cable, and as you can see, the cable is oscillating with a superposition of different modal contributions. On the right, the Stockbridge damper performs as expected. The forcing frequency and natural frequency of the damper are in resonance, and the cable's motion has almost been eliminated. Let's see now how the damper performs with a forcing frequency not equal to its natural frequency. Here is the results for an external force with a frequency equal to mode 2 of the cable. As you can see, the damper does not eliminate vibrations in the cable. However, the amplitude of vibrations have still been reduced.
Some of the limitations of Jacob's simulation include: firstly, difficulties reproducing results using cable elements instead of beams. Secondly, higher sample rates required large computation times. Finally, solutions did not converge to analytical predictions at higher modes. So computer models are fine, but can a Stockbridge damper actually reduce vibration? I'll let our handyman John show us how he and his build team tested whether they can.
For the final part of our project, the build team set about physically comparing damped and undamped vibration. We used a pre-built testing rig that held a steel cable looped at each end and tensioned with a chain ratchet. To initiate vibration, we used an electromagnetic shaker clamped to the cable and a frequency generator to apply a constant excitation force. The dog bone damper consists of 2 irregular masses at an angular offset. The offset introduces torsional damping that dissipates more energy and is particularly useful in 3-dimensional applications such as Aeolian vibration. The Salvi damper has the 2 masses centered in the vertical plane, and although it lacks the torsional vibration mode, it was still effective over a considerable range of frequencies. The undamped testing wasn't able to distinguish anything past mode 3, and we were only able to get decent damping comparisons in mode 1 because the amplitudes at higher modes just became too small. Let's run through the footage. Here we can see the first mode of vibration for the undamped cable.
It's the one and only Digo Double G.
At the anti-node of the first mode, the cable is vibrating with an amplitude of approximately 50 mil, as shown here. This is the cable now vibrating in the second mode, despite it being hard to see. Vibration at the approximate node and antinode for mode 2 are now shown on the screen. The maximum displacement was about 3 mm. The last discernible mode, mode 3, is shown here. The approximate node and antinode vibration are on the screen. Again, the maximum cable displacement was about 3 mm. With the dog bone damper attached, a frequency sweep was performed. As you can see, the amplitude of the vibration has been significantly reduced. The largest response in the dog bone damper occurred at about 8 Hz, and this vibration is shown here. As you can see from the overhead shot, out-of-plane vibration has been induced by the angular offset of mass in the dog bone damper. With the Selby damper attached to the cable, another frequency sweep was performed. The amplitude of vibration has again been significantly reduced. The largest response in the Selby damper occurred at about 10 Hz. This vibration is shown on the screen here. Finally, here's a comparison of the antinode vibration at mode 1 between the damped and undamped systems. As you can see, the dampers have worked effectively to reduce the vibration in the cable. We had to deal with a number of limitations and inaccuracies with the physical model. The major ones being that the chain ratchet and connections would have been included in the vibration response. The shaker clamp acts as a type of fixed point instead of a simple applied load. The frequency generator dial was scaled unevenly and was inaccurate between 8 and 20 Hz. And we weren't able to show the effect of positioning the damper at a node point because we were limited to mode 1. As a recap, the analytical, experimental, and simulated natural frequencies are compared here, along with the changes in amplitude and resonant points of the two dampers. The similarity between these values gives credibility to our testing, despite the limitations that we faced. After all of this, we have confirmed that the dampers work, as you've all just seen.
Well, that settles that. I guess they really do work.
Guess so. Thanks so much, Mr. Energetic Sky.
No worries, fellas.
Hey! Looks like the power's back on.
Oh, sweet. It's time to get back to sports.
Anyway, boys, looks like my job here is done. I'll catch you later, fellas. Cheers.
Cheers.
Time for smoke, eh?